Celsius. The grams will cancel out, degrees Celsius will cancel out, and I'll be left with joules. So I have 200 times 0.9 times 125. Oh, nope, sorry, not 125. What is the change in temperature for that first region?
10, 1800. Joules.
Yep. So phase one, 1800 joules. Or phase. All right, in section 3, we're skipping over the melting bit for now. Yes,
Is it negative 10 or just 10? Or-
final minus initial, so it's 0 minus negative 10, so it should be positive. Are you good with that? All right, section 3, part 3, whichever one you want to do.
How much room do we need to leave between 1 and 3?
It's basically, once we get the formula down, it's 2 lines.
Okay.
Kind of like that. Again, it's staying liquid water during this entire slope here. So I have MC delta T. So it's 200 grams times specific heat of water, liquid, 4.184 joules per gram degrees Celsius, times, what is the change in temperature in the third section?
100.
You sound unsure.
100. 100.
There we go, that sounds much more sure. Then we multiply that out, and we get 8, 3, 6, 8. Then
0. Joules.
so it takes that amount in order to get it up to, from just melted up to ready to boil. 836. And then phase 5, or part 5, that is the part, the last part, where we're not having a change in phase, it stays steam throughout this entire slope here. And so the mass is still 200 grams. Specific heat of steam, 2.01 joules. Oh, there's a mistake.
Do we use the wrong number?
It's not 0.9, that's aluminum. For ice, it is 2.089.
$4,178 joules.
4,100.
And 78 joules. And that'd be 15 degrees Celsius. $6,000 and 30 joules.
6,030.
6,000.
Point.
Doing it wrong.
Ice, so 2.1. No, okay, no, there's no actual right. All right, so now what do we do about the phase of, change of phase, not phase of change? So as we get to melt, we're starting to take, we've got this solid water, ice. The molecules are starting to move a little bit, not enough really to cause any damage, but they are starting to move. But when you get to here, they will start to separate noticeably. There is no change in temperature when it melts. There's no change in temperature when it boils. So whatever formula we have, it cannot take change in temperature into account. Other than that, it looks very similar to what we just did. It's not MC delta T anymore for phase change. So if I have solid, liquid, gas, so any one of those, we use what is known as the latent heat. If I am going from liquid to gas or gas to liquid, so if I'm going from between, actually, liquid and solid, let's do that one. If I'm going between liquid and solid, if I'm going from solid to liquid, it's called melting. If I'm going from, make sure I said that right, going solid to liquid, I'm melting. If I'm going from liquid to solid, I'm freezing, but they don't call it the latent heat of freezing. They actually call it latent heat of fusion. As things get fused together, in other words, they basically get bonded and stuck together. So L sub F, this would be the latent heat of fusion. If there were a latent heat of melting, it would be the exact same number. And so the energy needed is going to be mass times the latent heat. So for section 2, the amount of energy is going to be 200 grams times the latent heat of fusion, which I need to look up because I don't remember what it is off the top of my head.
Is that only for solid to liquid? Or you said it's the same if it's from liquid to solid?
Solid to liquid or liquid to solid. Some textbooks will have they'll have one value positive, one value negative, but if you just think through, I don't think you need to bother with that. So, in order to melt it, I need to add energy in. In order to freeze it, I have to take energy out.
Oh, okay. One's in, one out.
Okay. Latent heat of fusion. It is 334 joules per gram. Latent heat of fusion of water. 300, and I think I said 34 joules per gram. So 200 times 334 joules per gram. So we end up with 66800 joules. Unless I meant Carol's, sorry. 66800. If I'm going from solid into gas, yes, I'm boiling in this particular case, but they go by vaporization. This is, I would use, so between liquid and gas, I use the latent heat of vaporization. LV for a liquid, or for water. Two 260 joules per gram. And so part 4 Q is equal to MLV, which is 200 grams times 2260 joules per gram.
452,000 joules.
And 452,000. So that is where most of the energy is going into it, and that is converting it from liquid into gas. We haven't answered the question, but we are almost there. The last little bit is how much energy is required to turn it into steam. Well, it's the sum of all of that, and we just add it together. Someone would be kind enough to add those.
Six, 1, 2, 6, 8, 8.
612
688.
688, and same thing back there, all right. Joules. All right, so over 500,000 joules. How much is that? Let's say I could take an ice cube at -10 degrees Celsius, keep it in my mouth long enough and turn it into steam. How many calories have I burned off? Well, let's do a conversion. So first thing I need to do is I need to convert this joules into the lowercase c calories, into science calories. So 612,688 joules. How many joules are in a calorie? Or how many calories in a joule?
That's all of it added up?
Yes, unless two people got that, I'm assuming that's correct. So joules in the calorie. Hewitt provides us on the back cover here, inside the back cover. It is energy. 1 calorie, lowercase c, is 4.184 joules. I know that 1 calorie, 4.184 joules. There are other ways of doing conversion, but
So that's the same number as the H2O.
Yes, yes indeed. The only difference between the two is this is calories and that's joules. I got two fractions equal to each other, so I multiply the diagonal I know, divide by what I have left over. And so the amount of energy is gonna be 612,688 divided by 4.184.
146435.
146435.
Yeah, 0.9465.
Calories. How many food calories is that?
It's a lot of calories. Way more than your daily intake.
Is it a lot of calories?
How much do you eat in a day? Like 2,000 calories?
Yeah, but that's food calories,
Okay.
not these calories.
Oh, yeah. I know the conversion.
How many lowercase c calories in a food calorie? Oh, I thought you
My
said.
hand hurt.
Oh, well, it sounded like the correct answer, so.
Are there 2 little calories in a big calorie? 1,000.
So 146.4394 food calories. So if I could do it, I could burn off 140, a little over 146 food calories.
It's not a good workout.
Now, if I could take an ice cube and get it up to the point where it turns into steam, I'm probably dead. Because I can't, it'd be very difficult for me to get that cube higher than my body temperature. Which is about 35 degrees Celsius. So I could get it up to 35 degrees Celsius. But that's probably about as far as I could go. But melting an ice cube, if you're counting calories, melting ice cubes, the energy has to come from somewhere.
So what's the difference between the calories? What, you said one of them is just a science method of measuring?
I'm not quite sure why that there's a distinction between the two. I mean, clearly there is. My speculation is that when the food scientists started counting calories, that they felt that
They want smaller numbers.
you should be eating 2 million calories a day, and I guess they figured 2,000 was easier for people to digest.
Okay.
No pun intended.
Ah.
That is my speculation. I'm really not quite sure why they decided to give it the same name yet have it mean something different. All right. Any questions? Because it's about to get depressing. Just give you a little heads up there. It might, the depressing part might show up on Tuesday, maybe today. At least I find it depressing. All right, so we've been talking about thermodynamics, and there are, of course, rules. We have Newton's laws of motion, we have Kepler's laws of planetary motion. We have 4 laws of thermodynamics. Starting off with the 0th law. Then there's the 1st law, 2nd law, and 3rd law. So I ask you, why 0th? Why didn't they just call this 1 through 4? Why 0 through 3?
Because it's physics.
Because what?
It's physics.
It was more that, there was more logic to it than that,
Okay.
as opposed to, we want people to wonder.
Uh-huh.
Why would you ever start with 0?
A definite baseline. I don't know.
Somewhat.
Somewhat.
Typically, if you were coming up with a law of thermodynamics and no one had done it before you, what would you call
You
Your
name it
law.
after yourself.
it? Oh, I was thinking in terms of numerically, what would you call it?
Oh,
Yeah, or the first law. And they did. So part of that is the 0th law came after the first law.
oh, okay.
Why call it the 0th law? Why not just put it like the 4th or put it wherever it fell in?
Because it happens before the first law.
It depends on what you mean by that.
Was it needed for the first one?
In a sense, I'll go ahead and, it's more fundamental.
Okay.
They consider this one to be the most fundamental, and then it gets more and more abstract as you go. All right, so the 0th law, any of you remember what the transitive law of equality is in mathematics? It's the fancy word, it's an obvious thing in math, but
Transitive law.
transitive law of equality.
Transition, something.
So, here's the transitive law of equality. It is earth-shattering. If A equals B and B equals C, then A equals C.
Oh, okay.
I know, you're looking at that going, why didn't anyone tell me this before? The reason I bring it up is the 0th law of thermodynamics is basically the same thing, except I'm gonna use more words. If A is in thermal equilibrium,